Welcome to Math 31. This is a lesson on higher derivatives or higher order derivatives. This is where we start looking at second and third derivatives, or even higher if necessary. And notation is an issue. Most of it's quite predictable. For the second derivative in this regular function notation, it'd be f double prime at x. This is the second derivative. Then in Leibniz notation, d squared y over dx squared. So you'll notice the position of the exponents. The numerator, the 2, is tucked in between the d and the y, and then the denominator follows the x. And the y double prime, of course, would work like that. And I guess I didn't write it on this on your notes, but you could also have d. I don't use this notation very often. D squared y x. And then the third derivative would be, predictably, f triple prime x, and then everything else goes the same way, including this. So the application for higher derivatives, you will run into particularly the second derivative a lot in this course when we get to applications and also graphing. And the most common one, let me get these out here. Yeah, didn't do a good job with that. But if we took a look at these three graphs, position versus time, and then the following ones, this is pretty common, right? This is a ball that's tossed into the air. Excuse the little gap in there. And this is the path that we would expect it to travel at. The ball goes up, reaches its maximum height at 2 seconds, then hits the ground at 4 seconds. Then the first derivative would be the speed, or in this case the velocity function, and it starts off with its maximum speed, and then it goes in a linear path right at this point t is equal to 2, right there. That's when its speed is, or its velocity is 0. And then it starts coming back down again, so its velocity is in the negative direction. But it is a linear path. And then the second derivative, so this would be s prime at t. So here's s at t, s prime at t, and then the second derivative s double prime at t. That. And this would represent the acceleration. And for those of you who are familiar with this physics application, the rate of acceleration does not change at all. It's always going to be negative 9.81. So we end up with a constant value for that. And you will be working with these a lot, starting with position, ending up with acceleration, starting with acceleration, ending up with position. So you've got to be fairly comfortable with it. But it should make sense, the different nature of these, even algebraically, how this is of form y is equal to x squared. It's a quadratic, negative x squared. Then this is y is equal to x, a linear graph. And then this is y is equal to a constant, which I'll just write as negative 9.81. So you're going down by 1 degree algebraically for a simple graph like this, or for simple functions like these. Acceleration is a constant value always. The velocity is not a constant value, but it's a linear function, and then the position is quadratic. It's changing at that rate. More of that later on, but first off, let's just do some fairly straightforward derivative questions. Here we want to get the second and the third derivative. And if it's a polynomial function, not a big deal. And of course, you have to get the first derivative to begin this whole thing. So the first derivative would be 12x to the 3 minus 21x squared plus 10x plus 2. The second derivative would be 36x squared minus 42x plus 10. So now we're down to a quadratic. And then the third derivative is equal to 72x minus 42. And then, of course, you could keep going at least one more derivative. Now, the nature of what the third derivative in particular means, if the second derivative represents acceleration starting with the position function, the third derivative which I better write properly in that one, would indicate the rate the acceleration is changing per second. Now that's a little harder to actually make sense of. So when you start getting to the third derivative, it gets a little more abstract. You're starting to, the rate the acceleration is changing. So that would mean a very dynamic system where not only is the speed changing constantly, which is what you would expect if you were driving and you didn't have cruise control. Your speed is fluctuating quite often. Acceleration would be changing as well. So you're constantly having your rate of change, because that's what the derivative represents, the rate of change of one variable with respect to another. So as a result, we don't work much with third derivatives. You'll be going up to the second derivative often, and that basically is it. So there is a pretty standard polynomial type one. The next question is finding the second derivative at x equal 1. So in order to work this one out, the same deal, we need to find out what the first derivative is initially. So the first derivative, we will can use the quotient rule. So u is equal to x, v is equal to x plus 1. Now this is not a complicated equation just because of the nature of the polynomials. U prime is equal to 1, v prime is also equal to 1. So y prime, as always, is equal to u prime v minus u v prime over v squared. So y prime is equal to u prime, which is 1, times x plus 1 minus u is x times v prime, which is 1, all over top of v squared. So x plus 1 to the 2. Cleaning this one up, y prime is equal to x plus 1 minus x over x plus 1 squared. So y prime is equal to 1 over x plus 1 to the 2. So y prime could also be written as x plus 1 to the negative 2. So now when we find the second derivative, we would use the chain rule. So y double prime is equal to negative 2 times x plus 1, subtract 1 is negative 3, multiplied by the derivative of the inner. So f double prime at x is equal to negative 2 times x plus 1 to the negative 3. Or if you preferred, the second derivative is negative 2 over x plus 1 to the 3. So this makes the next part fairly routine. F double prime at 1, which is what we want, is negative 2 over 1 plus 1 cubed. So the second derivative at x equal 1 is negative 2 over 2 cubed is 8. So the second derivative is equal to negative 1 over 4. So if you thought of that first graph, f at x being a function of position is a function of time, this would represent the acceleration at x is equal to 1, or t is equal to 1. Now where these ones get complicated, unfortunately, is when you start getting implicit differentiation involved. So we now want to get the second derivative of this xy function where you don't have the explicit y defined explicitly in terms of x. So we do it the way we always do. We get the first derivative. So with care, 3y cubed would be 3y squared times y prime minus, now with the product rule, the derivative of x is 1. We've seen this version before, times y, and then plus x stays as it is, take the derivative of y, and it's y prime. And then this is equal to 0. So 3y squared, y prime, minus y, minus x y prime is equal to 0. Y primes can stay on the left, so 3y squared y prime minus xy prime is equal to y. Factor out the y primes, and we'll get 3y squared minus x is equal to y. So y prime is equal to y over 3y squared minus x. Now that's fine and dandy as far as it goes. Sadly, we need a little bit more, though, with this problem. We need the second derivative. Now, to get y double prime, we will have to use the quotient rule. Or else, we could use the chain rule in conjunction with the product rule if we wanted to take that denominator up. So I'm going to use u and v notation. So u is equal to y, so u prime is equal to y prime. So as always with implicit differentiation, when you're taking it with respect to x or to a different variable, the only way you can indicate that is y prime or dy dx. And then v is equal to 3y squared minus x, so v prime is equal to 6y, y prime minus 1. So therefore, the second derivative will be equal to u prime v minus u v prime over v squared. And now we substitute everything in with considerable care. So I'm going to bring up a new screen to get a little bit of space. So the second derivative, I'll indicate it like that, equal to u prime. So that's y prime times v, which is 3y squared minus x, minus u, which is simply y, multiplied by v prime, which we've got to be 6y, y prime, minus 1, and then this is all over v squared. So 3y squared minus x to the 2. I'm just going to take this back for a second to make sure I wrote it all down right. Looks good. Now you see the problem probably as quickly as I do. It's one thing to define the second derivative in terms of y, and that's typical with all implicit differentiation, where the answer, the derivative, will often have both x and y variables in it. But you cannot have it with a y prime in there. So these y primes have to be replaced and substituted in. So y prime, according to what we had earlier, is equal to y over 3y squared minus x. So I go into this function and I do the replacement. Now you're probably thinking, should you do it now or should you do it later? Good question. The thing of it is that if we replace it in now, we will get a slightly cleaner equation as a result of this. And if you did it later, also works too. So it's really a judgment call. Most people prefer to put it in earlier, particularly when you look at the question and you see the y prime with 3y squared minus x. We're going to get a cancellation at the start. So if you do a quick size up of it, you might well prefer to do this. But you have to be very careful. So replace the y prime with y over 3y squared minus x, and this then gets multiplied by 3y squared minus x. And then subtract y times 6y, y prime. Now, you may well decide to multiply or distribute that y in. That would be fine. I'm not. I would write 6y, then y prime, replace it with y over 3y squared minus x, and then minus 1. And then this is all over v squared, which is 3y squared minus x to the 2. Now we do get this cancellation, which is good. So the second derivative is equal to simply y minus, now I'm going to distribute this y in right away. So I will get minus 6y to the 3. That was just a judgment call, wasn't necessary, over 3y squared minus x. Wouldn't have made a lot of difference. You could have simplified first, but there's not much going on. That's a pretty simple expression. And then plus y. And this is all over your v squared or your 3y squared minus x to the 2. Now, unfortunately, that's not y minus y, so they don't cancel out. So we need now to get a common denominator with this one. Or we can get rid of that 3y squared minus x, deal with the complex fraction in that other method we've been looking at. Instead of getting a common denominator and then dividing out, remember, we can just multiply every term by 3y squared minus x and then do the same thing on the bottom, because that's just multiplying by a factor of 1. So that'll mean the denominator is 3y squared minus x to the 3. And then when we multiply that 3y squared minus x by each of the terms, we end up getting, it's going to cancel for the middle one, which is good. We'll get y times 3y, or hang on, before I do that, we should write that as 2y. So let's be a little smart about this. Y plus y is 2y, and then 3y squared minus x.